Hello. In last lecture, we covered the Moore state machine, and we convert the circuit, the digital sequential circuit, into a state diagram, state machine. And in this lecture, we are going to try to convert it back from a state machine to a digital circuit. So this is more practical because you can imagine that when you are designing a digital system, you know what the states are and all these transitioning conditions, and you can draw the state diagram and then convert the diagram to a truth table and further into a digital circuits, which will be the real hardware can do the job. So after that, we are going to cover two examples about the Mealy state machine as well. And that's pretty much everything about the state machine we're going to cover in this class. So let's start with the example first. It's going to be a diagram to a circuit. So the state diagram looks like this. And you know it's a Moore state machine because you have both the states and the output in the bubble at the same time, right? So these are the inputs. I didn't write the x over here, x equals, but you should know that these are the inputs to trigger the transition. All right, so that's a state diagram. That's a Moore state machine. And let's start converting this to the digital circuit, to the sequential circuit. So step one, convert it into a truth table. X, Q1, Q2. And what you have over here are Q1 prime, Q2 prime, Y, Y prime. So these are the next states. Q1 prime, Q2 prime, and Y prime. And you must be wondering, hey, in the previous examples, we did a JK flip-flop, we did a T flip-flop, and you have a T here, have a JK here, but why this one doesn't have the T and JK? How do you know it doesn't have it? So the reason it doesn't have it is because we are trying to use the D flip-flop. It's not, there's no function applied to the D flip-flop because the D flip-flop is going to directly transfer whatever at D, which is the input, to the Q. So that's why D equals to Q. So we don't have to list all the functions and key maps or truth tables to convert it. And so that's why we do not have intermediate variable over here because we know they are equal. So we prefer using D flip-flops when we are converting the state diagram into a circuit. It's easier to think about to find out the results. Okay. So we know the inputs are, of course, 0, 0, 0. All right. And the next step is to look for Q1 prime, Q2 prime, and Y prime. So what is Q1 prime? Q1 prime, the problem is we don't know that yet. The reason is we don't have any Boolean algebra expressions to derive from, right? So the only thing given here is the 0 and 1, the states, or the conditions as well. So when you know the 0 and 1s, you want to convert it into an expression. So something comes to your mind. What is that? Right, K-map. So the inputs are X, Q1, Q2, 0, 1. That's the two conditions of X. And here's 0, 0, 0, 1, 1, 1, 1, 0. And now let's see. For Q1 prime, when X is 0, Q1, Q2 are zeros, And you know that because this is a Moore state machine. So when Q1 and Q2 are zeros, the Y has to be 1. And you note that, right? So for this one as well, just write it down here. And when X is 1, but now X is 0. So when X is 0, it jumps to 0, 1 state. And the output becomes 0. That's a Y prime. Because when Q1 and Q2 are 0, 1, the Y will be 0 because 0, 1, 0 here, that's a Moore state machine. The output only depends on the states, right? And now let's look at the next. Q1, Q2, 0, 1 here. So Y has to be 0. And when X is 0, it jumps to 1, 1. And the output will be 0. 1, 0. Y will be 0. And when X is 0, it jumps to 0, 1. And Y is 0. Right? And 1, 1, when X is 0 or 1, doesn't matter. It's going to stay at this state. It's going to stuck here. You see, whenever it jumps to this state, so whatever the input is, right, it's going to stay here. It's like a dead loop. So when Q1, Q2 is 1, the output has to be 1, and Y has to be 0. Okay? 0, 0, and X is 1, it jumps to 1, 0, and Y is 0. For 0, 1, when X is 1, it jumps to 1, 0, and Y becomes 0. And originally, because it's 0, 1, so Y originally was 0 over there. And look at this next. 1, 0, 1, 0, Y has to be 0, and X is 1, jumps to 0, 0, and Y becomes 1. 1, 1, same stuff, same story, right? It's going to stay here, and Y has to be 0 all the time. That's the final result. Let me double check comparisons to the nodes really quick, just in case I'm making any mistakes. Hopefully not, because it's going to affect all the following calculations. It's going to waste of time. So it looks like they are all right. All right. So let's get Q1 prime. Q1 prime, let's transfer the 1 zeros into this K-map so we can derive for Q1 prime. Q1 prime, you have 3 zeros. They are at 0, 0, 0 and 0, 1, 0 and 1, 1, 0. So all the rest of them are ones. Okay, so group them and group these two. So Q1 prime equals to X Q1 naught or Q2. That's Q1 prime. What about Q2 prime? For Q2 prime, you are getting so 3 zeros are here, 1, 0, 0, 1, 0, 1, and 1, 1, 0. So all the rest of them are ones. And you can group this 4 and this 2. So Q2 prime equals to X naught or Q1, Q2. X naught or Q1, Q2. All right. What about Y? Y equals to, have to do the same job for Y. And you can find out there are two ones, 0, 0, 0, and 1, 0, 0. So group them, you're getting Q1 not, Q2 not. Be careful, this is not Q1, Q2 none. Right? So this is Q1 not and Q2 not. Do we need a Q? Do we need a one Y prime over here? We don't, because after we get Y and all the Qs, we can do a D flip-flop circuit. We're done. Okay. So let's try to draw it. So that's step one. Step two, we can start drawing this sequential circuit. And X is the input. And we are assuming we are using D flip-flops. Q1, D2, Q2, that's Q1 bar, Q2 bar. So Q1 equals to Q1 not. So this has to be inverted first before it goes to that AND gate. So that's unlogic or Q2. Okay, so that's Q1 prime. It goes to D1. After the clock, it's going to be transferred to Q1, becomes Q1 prime, the next state of Q1. So we're done for Q1 prime. What about Q2 prime? Q2 prime is X not inverted or Q1 and Q2. Q1 and Q2. So that's Q1 and that's Q2. Don't have too much space. Q1 and Q2 or X naught. All right, go back to D2. And the Y, which is Q1 naught and Q2 naught. All right, so that's the entire sequential circuit comes from this state machine. Okay, so now we have practiced the Moore state machine, starting from the state diagram to the sequential logic circuit, and also from the circuit to the state diagram. It's back and forth. So whenever you see something like this, it's actually pretty straightforward. You can directly solve it using the methods we introduced in the class. Okay, so now let's start dealing with Mealy. Mealy circuit. Mealy state machine. It's actually super easy to identify if it's a Mealy or a Moore state machine, because you can directly see if the input is being injected into the output, the combinational logic of the output. So let's take a look at the pretty much a very similar example from the first one we introduced in the last lecture and convert, and we just modify it into a Mealy state machine. So first, still, we convert it from a circuit to a diagram. We got an unlogic, and A is here, and we got a T flip-flop. And also we have another T flip-flop over here. That's the OR logic. The input is A naught. Another input is QA. QB comes back, get into the AND gate of the input, and this goes to TA. And the last one, so A will come forward to the output and OR with QB naught. You can see that the final output here is not just being affected by the Qs here, right? But also being affected by the input as well. So this is the Mealy state machine. It's super simple to identify as a Mealy or Moore, right? But now let's look at the rules about how to convert it into a state diagram. Still the same concept. Step one should be a true stable, always. So let's see, A, QB. And what are these intermediate variables? So you've got QA next state, QB next state, TA, TB, Y prime, right? So the same combinations. And what's the next step? Yeah, I have to find out the true stables, right? The logic expressions. So what is QA prime? So QA comes from this T flip-flop. So we know that it totally depends on the T. So when T is 0, it's going to copy. When T is 1, it's going to toggle. Same to QB because it's also a T flip-flop. Copy, toggle. Change the marker. So that's QA prime, QB prime. And also TA, what is TA? TA is QB and A. That's just A and QB. TB is A naught or QA. What about the the very last one, which is Y and Y prime. So Y is A or QB naught. Y prime is A or QB naught next state. Okay. Let's start filling into the true stable over here. So Q1 prime, which is depends on QA and T. So we need to know T first. So T is A and QB. A and QB, which is TA. A and QB 0, 0, 0, 0, 0, 1, 0, 1. Okay. TB, A naught or QA. A naught or QA. A naught or QA. 1, 1. Wait, TB, A naught or QA. A naught or QA. 1, 1. A naught or QA 0, 0, 1, 1. Double check. Yeah, that's right. And Y will be A or QB naught. A or QB naught. 1, 0, 1, 0, 1, 1, 1, 1. Is this right? 1, 0, 1, 0, 4, 1. Yes, this is right. So after that, since we know all the T's, so it's pretty easy to determine the QA prime and QB prime. So when TA is 0, QA will memorize the previous QA state. So it's going to be 0, memorize, toggle, memorize, toggle. Wait, the second should be 1? No, it's 0. TA. Why did I put a 1 in my notes? That's not right. All right, never mind. It should be 0, right? Because because QA prime is a T flip-flop. So when TA is 0, it should memorize the previous state. So I think I made a mistake in my notes. So this should be 0. Sorry. Okay.
And here
QB prime.
you got an OR gate, and that's Q1.
This memorize, right? So this is right. So TP
gate.
toggle.
And here is a P
0 1 0 0 memorize.
This.
Memorize.
And here is a NAND gate. NAND gate has
toggle 1 toggle QB 101. All right, we're pretty much done here. Y prime will be A or QB next state. A or QB next state. A or QB not. A or QB not. So A or QB not. Only you have 0, 1, you're getting a 0, but all the other ones should be 1s. So only two zeros. All right. So it's pretty close to the conclusion over here. What we need to do next, step 2, right? Convert this guy into the state diagram. That's what we want to do. So, but that's a Mealy machine, which means it's going to be slightly different. Now let's take a look what that looks like. Step 2. So we only want to keep the states into the circle. So for example, the first state, which is 0, 0. And on the arc, we want to include the input and y prime. So it's going to be A, y prime, the next state of y. Because it's trying to tell people when, for example, you are thinking about a practical circuit. It jumps from a state to another state, and it's going to output a signal. So that signal is not affecting all the states. It's just trying to output an indicator or something, trying to let you know what just happened, right? So you need y prime but not y because the state has been transitioned to another state. So you need to output the very last result of the transition, which is y prime, not y. So that's why I need a y prime over here. So from 0, 0 to 0, 1, 0, 0 to 0, 1. And what you need A to be 0 and your y prime to be 0. Okay, this is how I'll do it. So that's A, that's y prime, A, y prime, A, y prime. Okay, so from 0, 0 to 0, 1. What about 0, 1 to 0, 0? Just transfer back. And you need A to be 0 and y prime to be 1. Right? And 1, 0 to 1, 1. 1, 0 to 1, 1. 1, 0 to 1, 1, you need A to be 0 and you need y prime to be 0 as well. 1, 1 to 1, 0. 1, 1 to 1, 0, you need A to be 0 and y prime to be 1. 0, 0 to 0, 0 itself. And you need A to be 1, you need y prime to be 1, right? And 0, 1 to 1, 1. 0, 1 to 1, 1. Where? 0, 1 to 1, 1. 0, 1 to 1, 1. I have to draw, yeah, for this. 0, 1 to 1. No, it's confusing. So 0, 1 to 1, 1. And A to be 1, y prime to be 1 as well. And 1, 0 to 1, 1. 1, 0 to 1, 1 again. So need it can be 1, 1 here. right? So instead of this, and this will work as well. And 11200, 11200, and it is 1 and 1. All right. So that's state diagram. This is not working. Not this one. So that's the final state diagram of this sequential circuit. I'm sorry, it's a little bit messy here. Let's look at what about the next? Can we convert a state diagram back to a circuit? Okay. Now let's look at the example here. Pretty similar circuit. So I have 1 0, 1 1, 0 1, 0 0. So this guy 0 0 will work. 1 0 will work as well. And you should know that. So the conditions are x and y prime. 0 0 and 0 0, 1 0, 1 1, 1 0, 0 0. That's pretty much everything. Should be included. Double check. Yeah, that's it. So step 1. Still truth table. X, Q1, Q2. It doesn't matter it's a Mealy or more. It's pretty simple always. Q1 prime, Q2 prime, Y prime. Why do we care about the Y prime? You know, because we only have Y prime over here. We don't have Y, right? But they satisfy the same logic though, because Y prime equals to blah blah, the function of Q1 prime, Q2 prime, and Y is a function of Q1 and Q2. And physically, Q1 is the same wire of Q1 prime in the circuit. It's just next state. It's just being expanded on the time domain. They are the same wire. Okay, no problem at all. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. And of course, we don't have all these log expressions yet. So now let's do it. Q1 prime. What is Q1 prime? We don't know. And we need to convert, put all these 1 zeros into the truth table and then to the K-map and then simplify it, right? So let's see. We have 0 0, 0 0. And when x is 0, it's going to 0 1. And the final output is 0. All right. When Q1, Q2 is 0 1, when x is 0, the output will be y, right? And it jumps to 1 1. And now for the next. When Q1, Q2 is 1 0, and when x is 0, y will be 0 and jumps to 0 1. When Q1, Q2 is 1 1, it's going to stop here. Doesn't matter. X is 1 0, right? So it's going to be 1 1, and the output will be 0 0, right? That's the final output. And when Q1, Q2 is 0 0, when x is 1, y will be 0. It jumps to 1 0. And when Q1, Q2 is 0 1, when x is 1, y will be 0 and jumps to 1 0. When Q1, Q2 is 1 0, and when x is 1, y will be 1, and the state will be 0 0. When Q1, Q2 is 1 1, same start, right? So it's going to stop here. and y will be 0. So that's the final truth table we can have. And let me double check if everything is right before we move forward. All right, so this is right. And we need a K-map to simplify it. So for Q1 prime, let's look at this. You only have 3 zeros. They are here, 0, 1, 0, here, and 1, 1, 0 here. So all the rest of them are ones. So this will be X Q1 naught, or that's Q2. That's Q1 prime. What about Q2 prime? Q2 prime, you have 3 zeros. They are 1, 0, 0, here 1, 0, 1, here 1, 1, 0, here, and all the rest of them are ones. Group them, group these two, and you are getting X naught or Q1, Q2. Okay. And next, Y prime. What is Y prime? You need the same stuff. 0, 1, 0, 0, 1, 1, 1, 1, 0. And you only have one term, so you don't need a K-map actually. 1, 1, 0. Only one, so it's going to be X. So it's going to be X, Q1, Q2 naught. Okay, so that's Y prime. So now we have all these signals. We know what are they. Now let's just start drawing the sequential circuit. We start from the signal which is X, and we have two states, Q1, Q2. So we need two D flip-flops. D1, Q1, Q1 naught. D2, Q2, Q2 naught. So Q1 prime, which is X, and Q1 naught, we need unlogic, or Q2. Q2 prime, which is X naught, or Q1 and Q2. Q1 and Q2. That's Q1, that's Q2, right? You and then or this guy. Next, Y prime. So Y prime is the same thing, right? So just Y, which is Q1. So you need X as well. It's a 3-input AND gate. But the thing is, you can AND these two first, and then AND this guy later. Okay. So that's the final sequential logic, and you can actually tell the difference because it's a Mealy state machine, and the final output is not only depends on the states, right? Not only the Qs, but also X. You see, X is being fed forward directly into the combinational logic of the output. So that's why this is a Mealy state machine. All right, hopefully after all these examples, you are able to do the homework. And if you have any questions, don't hesitate to ask me. And that's everything for state machine we're going to cover in this class. Thanks for watching, and I'm going to see you in the next video.